In the microservices system, services need a way to trust each other without checking a database every single time. This is why we use JSON Web Tokens or JWTs. They are the standard way to send information between the client and the server or between two services in a way that can be verified. But there's a problem. Most developers use JWTs every day, but very few actually understand how the specification works. Because of that, many applications are vulnerable to simple attacks. So in this video, we are going to look under the hood. We aren't just going to use a library. We are going to learn the entire JWT framework, which stands for JSON Object Signing and Encryption. We will cover how they are structured and the exact rules you need to follow so your microservices stay secure. So let's do it. Well, to understand why we use JWTs, we first have to look at the problem with traditional sessions. In the basic setup, when the user logs in, the server creates a session and stores it in its memory or database. The server then gives the user a session ID. Every time the user sends a request, the server has to look up that ID in its database to see who the user is. Well, this works fine for one server, but in a microservices architecture, you have many different services, like a billing service or an inventory service and a user service. If the billing service gets a request, it shouldn't have to call the user service or check a central database just to verify who the user is. That creates a bottleneck. It makes the system slow and hard to scale. JWT solves this by being stateless. Instead of storing a session ID and looking it up later, the server puts all the user's information like the user ID and the roles directly into a token. This token is then signed with a secret key, so it cannot be changed. Now that the user carries their own data with them, when they send a token to any services in your system, that service can verify the signature and trust the information inside it immediately. It doesn't need to ask a database. It doesn't need to ask another service. The token itself is the proof. This standard was developed by the JWT group, which stands for JSON Object Signing and Encryption. They started this work because we needed a simple JSON-based way to handle security across different systems and programming languages. Now that you know what the JWT is and why we need them, we need to look at how they are actually used in real world, from keeping your login sessions active to connecting different apps together. Now that we have the foundation, let's talk about where you actually see JWTs in real world. There are two main ways they are used: stateless sessions and federated identity. The most common use is storing session data directly on the client instead of a server database. Imagine an application where the server needs to know your user role, like if you're an admin or a regular user, to let you see certain pages. The traditional way is that server looks up your ID in a database on every single click to see if you are an admin. But with the JWT, server puts role equals admin attribute inside the JWT and gives it to you. Now every time you click a button, the server just looks at the token. Because the data is on the client, the server doesn't have to look anything up. This makes your app much faster and easier to scale. However, you have to be careful with security. If you store a JWT in a browser cookie, you have to protect it from CSRF or cross-site request forgery. And if you store it in local storage, you have to protect it from XSS or cross-site scripting. The second way is for login with Google buttons. This is called federated identity and is handled by a standard called OpenID Connect or OIDC. OIDC is a layer built on top of another framework called OAuth version 2. Its whole job is to use JWTs to share your identity. In the setup, you have three players: you, the app, and the identity provider like Google. The app sends you to Google to log in, Google verifies who you are, and sends a JWT back to the app. This is especially called an ID token. This ID token contains claims, assertions like the user's email is john@sunexample.com. The app trusts this information because Google signed it. This is how single sign-on works. You log in once, and Google issues the JWT ID tokens to any app you want to use, so you don't have to create a new password for every site. Now, within the systems, you will often hear about two types of tokens. First one is access token. These are short-lived, usually lasting 15 minutes, and you're used to actually get data from a server. These are often JWTs. Also, there are refresh tokens. These are long-lived and are used to get a new access token once the old one expires. These usually are not JWTs because the server needs to check a database every time to make sure your account hasn't been banned or deleted. It sounds simple so far, but to actually build this safely, you have to understand exactly what is inside this string of characters. Let's break down the three specific parts that make up every JWT. Every JWT is made of three parts, separated by dots. It looks like a long string of random characters, but it is actually just JSON data that has been encoded. The first part is the header. This is a small JSON object that tells the server how to read the token. It contains the type, which is almost always JWT, and the alg, which is the algorithm used to sign the token. It can also include CTY or content type if you're putting a JWT inside another JWT. The second part is payload. This is where the actual data or claims live. There are some registered claims defined by the official standard. They use three-letter names to save space. ISS is the issuer or who created the token. Sub is the subject, usually the user ID. AUD is the audience, or who is supposed to receive the token. EXP is the expiration time. NBF stands for not before the time the token starts being valid. IAT is issued at the time of creation. JTI is a unique JWT ID used to prevent replay attacks. You can also add public claims meant for general use, like a username, or private claims for your own specific apps, like a membership level. The third part is the signature. This is the security layer. It takes the header and the payload and runs them through a mathematical function with a secret key. It uses a signing algorithm, which is the one specified in the add claim. Depending on the algorithm, you use either a secret key, which is a single password shared between systems, or a private key, which is part of a public-private key pair used in more complex security setups. So to recap, let's go through the actual flow. When the user logs in, the server creates a JWT and sends it back to the client. The client then stores this token and includes it in the header of every future request it makes to the server. When the server receives a request, it doesn't need to check a database. Instead, it pulls the JWT from the header, decodes it, and uses its own secret key to recalculate the signature. If the signature it calculates matches the signature on the token, the server knows the user is who they claim to be and the data hasn't been changed. If a hacker changes even one letter in the payload, the signature will no longer match, and the server will reject the token immediately. The reason a JWT is safe to put in a URL is base64 URL encoding. This turns JSON into text by swapping characters. Finally, there's a concept called unsecured JWTs. These use the header algorithm equals to none and have no signature at all. They look like two blocks of text followed by a dot. These are very dangerous because anyone can change the data inside. You should almost never use them for security. To work with the JWT, you follow a simple process of encoding and decoding. To create an unsecured token, you take your JSON header and your JSON payload and convert them into UTF-8 bytes. Then you encode those bytes using the base64 method we discussed and join them together with a dot. However, in a real application, you don't just decode the data. You must verify it. This means your code looks at the signature or encryption data to prove the token is authentic before you trust any of the information it contains. Now that you see the full structure and the flow, we need to look at the specific technology that makes the signature verification possible, JWS or JSON Web Signatures. To understand the relationship between JWT and JWS, you can think of it like this. JWT is the container and the JWS is the tool used to lock it. When you look at a typical signed JWT, you see three parts separated by dots. The first two parts are the header and the payload, and the final part appearing after the last dot is the signature. JWS or JSON Web Signature is the specific standard that defines how that signature is created. It is the process we use to take the header and the payload, run them through a mathematical function with a key, and produce that final string of characters. So while the signature is the last part of the token you see, JWS is the specification that makes that part possible. It ensures integrity, meaning that data hasn't been changed, and the authenticity, meaning we know who sent it. It is important to remember that a signature does not hide your data. It only proves it's real. Anyone who sees a token can still read your claims. These are three main types of algorithm used to sign these tokens. We got HS256, which is symmetric. This uses a single shared secret like a long password. Both the server that creates the token and the server that verifies it must know this exact secret. It is simple and fast, but you have to be very careful about who you share your secret with. The other one is RS256, which is asymmetric. This uses a public-private key pair. The server creates the token using a private key, but anyone else can verify it using a public key. This is perfect for microservices because you can give the public key to every service in your system without worrying about them creating fake tokens. And the last one is ES256, which uses elliptic curve. This is similar to RSA but uses a different math. It provides the same level of security but with much smaller keys, which makes it faster and more efficient for mobile devices or limited hardware. JWS header can include extra information like a KID or key ID, which is a label that tells the server exactly which key was used. You might also see JWK or JKU, which provides the key or a link to the key directly in the header. While we usually see JWTs as a single string with two dots, there is another format called JWS JSON serialization. This format allows a single token to have multiple signatures. For example, you might want a token to be signed by both an identity service and a security firewall. It uses a JSON object instead of a dot-separated string, making it more flexible but less compact. A critical security rule when working with JWS is to always perform algorithm verification. You should explicitly tell your library to only accept the specific algorithm you expect, like RS256. This prevents hackers from changing the header to none or switching from a public key to a shared secret to bypass your security. Now, signing is great for proving who sent the data, but sometimes proving authenticity isn't enough. If your token contains sensitive data that no one else should see, we need to move from signing to encryption. Let's look at how JWE or JSON Web Encryption hides your data completely. JWS focuses on proving that the token is real, but JWE or JSON Web Encryption focuses on keeping the data secret. If you use JWS, anyone can read your data. If you use JWE, the data becomes opaque, meaning it looks like a string of random characters that no one can read without the secret key. In JWS, you sign with a private key so that everyone with the public key can verify it. In JWE, anyone with the public key can encrypt the data, but only the person with the private key can decrypt and read it. Another major difference is that JWE provides confidentiality, but it doesn't always prove who sent the token. Because of this, developers often use nested JWTs. This is where you sign a token first to prove your identity, and then you wrap that signed token inside an encrypted one. This gives you both integrity and secrecy. It also prevents signature removal attacks because the signature itself is hidden within the encrypted ciphertext. Because encryption is more complex than signing, a JWT token has 5 parts instead of 3, all separated by dots. First one is a protected header, which tells the server which algorithms are being used. Second one is the encrypted key. This is a specific key used to encrypt the payload, which itself is encrypted so only the recipient can see it. Third one is the initialization vector, or IV. This is a random data used to make sure that the same information doesn't result in same encrypted text twice. The next one is ciphertext, which is the actual encrypted payload. And finally, there is authentication tag, which is used to make sure that encrypted text hasn't been messed with. JWE uses 2 layers of protection. First, it picks a content encryption key to scramble your data. Then it protects the key itself. You can do this through key encryption, where you encrypt the key with the recipient's public key, or direct encryption, where you use a pre-shared password that both sides already know. For the actual scrambling of the data, JWS uses AES algorithms, which are the industry standard for high-speed encryption. Just like with JWS, you can also represent JWE in 2 ways. There is the compact serialization, which is a 5-part string, and there is also JSON serialization, which allows you to encrypt the same data for multiple people at once. Each person gets their own encrypted key part, so they can unlock the same hidden message. Now we know how to sign the tokens and how to encrypt them. But for all of this to work, both sides need a way to share their keys in a standard format. This brings us to JWK, or JSON Web Keys. A JWK is a standard way to represent a cryptographic key as a JSON object. Before this standard existed, sharing keys was messy because different systems use different file formats. With JWK, whether you are using RSA key, an elliptic curve key, or a simple shared secret, it all looks like a clean JSON structure that any programming language can understand. Every JWK has a few common fields that tell the server what it's looking at. The most important one is KTY, or key type. This tells you the family of the key. For example, if it's an RSA key, or an elliptic curve key, or a symmetric key. You will also see the use field, which tells you if the key is meant for signing or encryption, and the alg field, which identifies the specific algorithm it was built for, like RS-256. One of the most useful fields is the KID, or key ID. This is a unique label for the key. When a server receives a JWT, it looks at the key ID in the token's header and then finds a matching key ID in its list of JWKs to verify the signature. Depending on the type of the key, the JSON object will include different mathematical details. For an RSA key, you will see values for modulus and exponent. For elliptic curve keys, you will see the x and y coordinates on the curve. This allows the server to recreate the key perfectly without needing extra files or complex conversation. In a real microservices environment, you often have more than one key. For example, you might be in the middle of rotating your keys, which is moving from an old one to a new one. To handle this, the specification allows for JWK sets. This is simply a JSON object that holds an array of multiple keys. Lots of identity providers like Google provide a public URL where they host their JWK sets. This way, any service in your system can hit that URL, download the list of currently valid public keys, and use them to verify the tokens coming in. The URL can be setting JKU or JWK set URL header claim. This makes key management automatic and much more secure. Well, we talked a lot about the structure of these tokens and the keys that lock them, but we haven't looked at the actual math that makes it all possible. So now let's dive in JWA or JSON Web algorithms to see the logic behind the encryption. Everything we discussed so far, from the 3-part structure to the security of the tokens, relies on a set of mathematical rules called JWA or JSON Web algorithms. Well, you should only know the basic logic that keeps them safe. First, there is base 64. This isn't actually encryption, it's a kind of encoding. It is just a way of rewriting your data so it's safe to send over the internet. It takes the JSON and turns it into a string of characters that won't break a URL by swapping out symbols. Next are the hash algorithms, specifically SHA-256. A hash function is like a digital fingerprint. You can give it a massive amount of data and it will give you a fixed left secret called a digest. It is designed to be a one-way street. You can easily create a fingerprint from the data, but you can never turn the fingerprint back to its original data. More importantly, even if you change just one comma in your code, the entire fingerprint changes completely. When we use these hashes for security, we use 3 main methods that we talked before. The simplest method is HMAC, using algorithms like HS256. The simplest method is HMAC using algorithms like HS256. It combines the hash function with a shared secret or a password. To verify the token, both the sender and the receiver must know the exact password. If they do, they can run the same math and see if their results match. RSA used in RS-256 is a bit more advanced. This is based on the fact that it is very easy for a computer to multiply two giant prime numbers together, but it is incredibly difficult and slow for a computer to do the opposite, taking a massive number and figuring out which two prime numbers created it. This difficulty is what allows you to have a public key for verifying and a private key for signing. Finally, there is ECDSA using ES-256. Instead of using giant prime numbers, it uses the geometry of a specific curve. By moving points around the curve using a scalar multiplication, it creates a signature that is just as strong as RSA but uses much smaller keys. This makes it faster and better for mobile apps or systems that need to handle thousands of tokens per second. Now let's wrap up everything we talked about. We've covered the entire life cycle of JSON Web Token, from its basic structure to the complex math that keeps it secure. We saw that JWTs are compact URL-safe containers used to pass claims between parties. They solve the massive headache of scaling microservices by being stateless. Instead of your service hitting a database to check a session ID, the user carries their own verified data right inside the token. We looked at the two main ways they show up in the real world: stateless sessions, where the client holds its own permissions, and federated identity, specifically using OpenID Connect. This is what allows you to log in with Google and move between different apps without re-entering your password. Then we talked about the structure of a JWT. Every signed JWT is a three-part string: the header, which defines the algorithm; the payload, which holds the registered claims like ISS, sub, and exp, along with any custom data you need; and the signature, which proves nothing has been tampered with. We also talked about JWS and JWE. Remember, JWS is about integrity. It proves the data is authentic, but is still readable. JWE is about confidentiality. It turns the data into a 5-part encrypted string that is completely opaque to anyone without a private key. And here you can see how these two are compared together. To manage all of this, we use JWTs, or JSON Web Keys. This is about how we share public keys so that our services can automatically rotate keys and verify signatures using a JWKS or JSON Web Key set endpoint. Finally, we explain the algorithms. Whether you're using any of those algorithms, the goal is the same: creating a digital lock that is computationally impossible to break. Now you know how these tokens are built, how they are signed, how they are encrypted, and how they are shared. We will discuss the security issues and common attacks in a separate video. If you find this video helpful, make sure to like the video and subscribe to the channel. Thanks for watching. See you in the next one.